My name is Dr. Farhan Riaz, and this is the computer vision course that I'm teaching at the National University of Sciences and Technology. I'm using the slides that have been prepared by Professor James Hayes as part of computer vision course that is being offered at Georgia Tech University. Now let us make the substitutions that we have derived over here in this equation. So E of 0, 0 as we have seen is 0, and the first derivative which is EU of 0, 0 and EV of 0, 0, they both are equal to 0, and we are only left with one term which is 1 by 2 U into V. E U U and basically this term, this matrix, and U into V. This is what we are left with when we are trying to estimate the corner detector. Now, once we make these substitutions into this particular equation, um, this is what we obtain over here. So basically, an estimation of E of UV can be done as UV, and then there is a matrix M, and then UV again. And this matrix is basically represented by this particular equation. And simply, we can write this matrix in this particular form. So using linear algebra, we have basically written this thing into this particular form, and then carrying on from there, this is what we have. This is a 2 by 2 matrix of image derivatives, and it is averaged in a neighborhood because of the window that we are using over here, where I of x is partial derivative of I with respect to x, and I of y is partial derivative of I with respect to y, and ix iy is the partial derivative of I with respect to x and y both. um, um, Now, from all the previous discussion, we can easily see that the surface E of UV, let us assume that it is a surface, it can be locally approximated in a quadratic form. And this is the form that we are talking about. So it can be approximated by a quadratic form, since if we just take one slice of this quadratic form, which means that this thing becomes a constant, then actually this becomes the equation of an ellipse. Now, if we perform diagonalization of this matrix X, which is nothing but a combination of second order derivatives, this is the form that we can come up to, which means that lambda 1 and lambda 2, they are the eigenvalues, and we can have the corresponding eigenvalues and eigenvectors. The axis length of the ellipse are determined by the eigenvalues. So this is the direction of the fastest change, and this is the direction of the slowest change. This is indicated by a stronger or a high eigenvalue, and this is signified by a smaller eigenvalue. So the eigenvalues that we obtain in the case of after diagonalization of this matrix M, they are very important. And as we know that M is basically a matrix that is a combination of second order derivatives, so we can easily come to a conclusion that these eigenvalues, they signify the direction of change, and lambda max corresponds to direction of the fastest change, and lambda minimum is the direction of the slowest change. Now, these eigenvalues are very important, as they convey a lot of information about the presence of corners or edges or the flat regions. So this is how we can plot the two different eigenvalues, lambda 1 and lambda 2. If both of these values are very high, which means that we are somewhere lying in this region where lambda 1 has a high value and lambda 2 also has a high value, so lambda 1 and lambda 2 both are large, then this is a point that is corresponding to a corner. And in this case, the value of E, which is the energy, of a corner, it increases in all directions. Well, if we have the two eigenvalues giving us very small magnitudes, and then we can easily say that E is almost constant in all directions, and there is no significant change as we move horizontally or vertically from that point on. And now there is one case where the eigenvalues are very different. One is this range of the eigenvalues for lambda 2, and which is a very large value of lambda 2 and a small value of lambda 1. And this is the region where lambda 1 is very large and lambda 2 is very small. So both of these regions, they correspond to the edge. One is corresponding to a vertical edge and one is corresponding to the horizontal edge. So we can easily see that that the matrix M that we obtain, which is a combination of the second order derivatives, we can take the eigenvalues of that particular matrix, and that can give us a lot of information about the presence of corners in the images. So given all this information, we can actually model a corner response function that is called as an R, that is equal to the determinant of M minus alpha times the trace of M square. And this can be simplified as lambda 1 lambda 2 minus alpha times lambda 1 plus lambda 2 square. This value, basically it's important to model this thing, because if we have an edge, we are not really concerned about it if it is a horizontal edge or a vertical edge. We are mainly interested in that window. Once we place that window at a particular location, we have variations in all directions. So that is our point of concern. That is the corner over here, and this this is a corner response function, such that this R is very small in a flat region. This R is less than 0 in the case of an edge, vertical or horizontal. We already don't want to classify those two things as different. And then once we have a corner, the R value is greater than 0. That is a point corresponding to a corner. So basically, once we aim to work on the Harris corner detector, there are three important steps that are being done. We compute the matrix M for each image window to get the cornerness scores at every pixel in the image. Then we find those points whose surrounding windows they gave us the large corner responses. So we basically set a threshold value. If the threshold value is exceeded, we will always classify it as a corner. And then we take the points of the local maxima, that is amongst all the selected corners. We then take the local maxima, that is we perform the non-maximum suppression. This is the second order matrix. It is optional. We can we are talking about the Harris detector, so we can basically perform a Gaussian filtering for smoothing the image, so that we can actually remove noise. There are some other noise sources. For example, if we have the salt and pepper noise, that can always yield to a very high cornerness at those particular locations where we have the spikes in the images, and but they are actually wrong. So we can optionally go for some pre-filtering strategies. For example, over here we are doing the Gaussian filtering of the images. Then we can then we have to calculate this matrix, and for that we need to calculate ix, iy, ix square, iy square, and all these values. Then the Harris cornerness function is calculated. This is the equation of the Harris cornerness function, and then this is followed by the non-maximum suppression in order to eventually find the corners.